Prediction, decision, control, lots of techniques, many different ways of stringing them together, deciding which technique to use, sounds very complicated. And thinking about how to implement a system like a global traffic management system with lots of self-driving cars certainly is extremely complex. But there's actually a machine which is doing many more complex things every day, and there are about 7 billion of them on this planet already. Obviously, I'm talking about the human brain. Not only does it do all the tasks that we've discussed in this course, it does them with a fairly uniform architecture. So the plasticity or uniform architecture of the brain looks something like this. I mean, there are a whole bunch of neurons, about 100 billion neurons in the brain, and if you look at the topmost layer of the brain, a few millimeters thick, it's called the neocortex, which is believed to be responsible for much of our conscious thought. The way it's organized is in bunches of neurons which are arranged in columns, so there's a vertical arrangement of neurons, and these neurons have connections vertically as well as horizontally across columns. That's very important. That's one element of that structure. Each neuron, on the other hand, looks something like this. Most of the white matter in one's brain is consisting of the connections between the neurons. The neuron body is actually a small fraction of that of the gray matter, which is there in the brain. And the connections between neurons look something like this. These are called dendrites, and this is the axon. And a dendrite connects to other neurons via synapses. Synapses, we've learned in the past decade, form very rapidly between neurons that are dendrites which are close to dendrites and axons which are close to each other, and can form in minutes and can decay over time and very rapidly as well. So this is another important feature of the brain. An abstract model of the neuron, which is what is used by hierarchical temporal memory, which is what we're going to talk about, which is a model of the brain propounded by Jeff Hawkins, and he talks about this in a recent talk at the International Symposium on Computer Architecture, funnily enough, just in June this year. So the model that he uses is an abstract model of a neuron, which looks a lot like a neural element in a neural network. However, it has some very important differences, and we'll explain this structure in the next few minutes as we go along. The first important feature of hierarchical temporal memory is that it relies on sparse representations, in particular sparse distributed representations. These are closely related to the sparse distributed memory that we discussed way back during the look lecture. Remember the properties of very long bit sequences of zeros and ones. In particular, if we have patterns of 1,000 bits in length, we learned that there's a very low chance that patterns differ in less than 450 places. So most of them are far apart in this sense. Most random patterns chosen at random are far apart. Now consider special types of patterns. This time we'll take 2,000 bits because that's the example that Jeff Hawkins uses in his lecture. So we have a pattern of 2,000 bits, but it's forced to have only 40 ones. So only 2% of these bits are ones, and we force that in a particular way, which we'll describe shortly. But if we do this, then let's see what happens. There's a very low chance of a random sparse pattern, that means another random pattern with only 40 ones, matching any of these ones, or matching a significant number of these 40 ones. Just imagine, if 20 of these ones have to match, then the chance is 1 by 2,000 multiplied by itself 20 times. Even if we drop all but 10 random positions out of these 40, right? Let's just, for example, we have a pattern which has 40 ones, but we decide to retain only 10 of them at random. And then think about another sparse pattern of 40 ones to start with. The chance that after dropping 10, all but 10 from that pattern and all but 10 from our first pattern, the chance that any of these 10 match is again very small, right? Again, it's sort of 1 by 2,000 multiplied by itself many times, and you can work that out. Please try to work it out, because I might even ask a question on this at some point. It's fairly simple arithmetic, not even as complex as what we did for the 0, 1 sequences in sparse distributed memory. Now this particular feature is exploited by hierarchical temporal memory in the following way. If you consider the bunch of neurons in the sheet of neurons in the brain, say, or models of the brain, and say these neurons are being activated by light intensity falling in a particular pattern, right? Then obviously a light intensity pattern won't have just 2% of it bright. It'll be many more pixels will be bright in this kind of an image. But what the sparse distributed representation does is it chooses the 40 brightest, in some sense that it's not the 40 brightest necessarily, but if a set of neurons is bright in this area, they will be inhibited by neurons which are bright nearby. So only one of these neurons out of this bunch which are bright will end up firing. And by forcing neurons to turn off because their neighborhood is also equally bright, we get a sparse representation for a otherwise fairly dense image. Now, it's not clear why this is important right now, but it'll become clear sort of in a few minutes. What happens is that the similar scene, say there's a similar scene, say this was a particular pattern, and you view another similar scene, it'll give this a very similar sparse pattern even after subsampling. So even after we get rid of 30 of the 40 ones, we'll still get a similar sparse pattern from two different instances of the same scene, or even similar scenes. However, if you see completely different scenes, the chance that the sparse patterns that we'll get match in a large number of positions is very small. And that's a very important part of this kind of representations. The key is the number of bits that we start with, the fact that we choose only a small number of them as ones, and randomly drop some of them each time. All these things put together make it very unlikely that dissimilar scenes will give the same sparse patterns, but similar scenes will very likely give the same sparse pattern, or sparse patterns that match each other.